Welcome back, Math 152. We're going to continue on with the normal distribution applications. And what we're going to do this time is kind of work backwards, back from the previous chapter when we were looking at discrete probability distributions, and especially the binomial distribution. So what we want to be able to do is kind of look and see if there's any way that we can approximate it instead of using that binomial formula. And I'll talk about that in just a second. So let's go back to what we were talking about of a binomial random variable. So a binomial random variable represents the number of successes in a series of independent trials. The sample proportion is found dividing by the number of successes by the number of trials. Since the sample proportion is approximately normally distributed whenever NP was greater than or equal to 10 and N1 minus P is greater than or equal to 10, we saw this from the 6.3 when we were just doing probabilities of sample proportions. Basically, we're going to say, oh, well, if it's normally distributed, maybe we can do something with binomials because we need a proportion. We've got kind of the same thing, and we're just going to develop it from there. So the number of successes is also approximately normally distributed under these conditions. Therefore, the normal curve can also be used to compute approximate probabilities for the binomial distribution. So you may ask yourself, well, why am I going to do this when I've got the binomial formula? This is actually if you have a large sample size, and if you're going to do this, you remember building out the binomial probability distribution gets kind of long for large N, and doing the cumulative, it kind of gets heavy calculation-wise. This is actually easier using the tables or normal CDF for technology to calculate this. But we have to do a couple of different things now. So let's look at this. Recall that if X is a binomial random variable with n trials and success probability, then you remember what our expected value was? We have a proportion and a size, then we would expect n times p to be the mean. That would be the expected value that we would have. 30% of 100, we would expect 30 of those to have that characteristics. What about the variance? Well, that is just the NPQ. Remember, the Q is the 1 minus P, the not P. That's the variance. The standard deviation is just the square root of N times P, 1 minus P. I know these things. I know proportion. I know when we're doing N trials based on that binomial random variable scenario that's always exactly 0, 1, 2, 3 up to the number of trials. Here I've got all the information I need. I know it's normally distributed whenever the NP is greater than or equal to 10. So I can use a normal distribution curve to approximate a binomial random variable. So binomial probabilities can be computed exactly using the techniques described earlier. If the number of trials is large, using these methods by hand is extremely difficult and time-consuming because many terms have to be calculated and added together. So if the following conditions are met, the binomial probabilities can be approximated using a normal distribution. You can use normal tables, and it's much quicker than actually going through the exact binomial calculation. Let X be a binomial random variable with n trials and success probability P. If n times P is greater than or equal to 10, n times 1 minus P is greater than or equal to 10, then X is approximately normal with mean n times P, standard deviation the square root of n times P times 1 minus P. The binomial distribution is discrete. When we calculated those using the formula NCX, P to the X, 1 minus P to the n minus X, that was discrete. Each one of those was calculated. The normal distribution is continuous. So we have to do, to get a better value, we're going to have to do a little bit of a correction, and it's called the continuity correction. So that's just an adjustment made when approximating a discrete distribution with a continuous one. So here's an example. Suppose a fair coin is tossed 100 times. Let x represent the number of heads that result. Then x has a binomial distribution, n is 100 trials, and success probability p is equal to 0.5. If I wanted to compute the probability that x is between 45 and 55, in other words 45 to 55 heads out of those 100 times, the probability will differ depending on whether the endpoints 45 and 55 are included. So what we're going to do is basically use a little bit of a correction here to make sure we get enough probability to add that extra area in. So here's a picture. Here's the 45 and the 55, and the areas of the rectangles corresponding to 45 and to 55 should be excluded. To approximate this probability with the normal curve, compute the area under the curve between 45.5 and 54.5. To compute the probability of 45 less than or equal to x, less than or equal to 55, the areas of the rectangles need to be included, so I'm going to back this thing off to 44.5 and to 55.5. So here's the little different rules of what I'm going to do to correct, and we're going to show this in just a minute. Okay. So let x be the number of heads that appear when a fair coin is tossed 100 times. Use the normal curve to find the probability that 45 is less than or equal to x, less than or equal to 55. Our equals are included. So when I go through, here's my n times p, that's the mean. 50 is expected. The standard deviation, NP, 1 minus P, that gives me 5. I've got these included, so I want to include the 45 and the 55. So I'm going to back this off to a 44.5, extend that out to 55.5, and then do my technology to find the probability of 7.7287. Okay. Here's some other situations. To approximate the probability of x less than or equal to 55, I want to open it up by 0.5. Bigger than 55, I want to back off to the other side, 54.5. And exactly 55, I'm going to calculate the probability between 55.5 and 54.5. So that gives me a little bit of an area to give me the exact value of the 55 exactly. So here is a drawing or a figure that kind of puts all of those different scenarios into one drawing. Here is if I wanted to have the probability of A less than or equal to X less than or equal to B, I'm going to subtract 0.5 from the A, add 0.5 to the B. X less than or equal to B, I want to add 0.5. Bigger than A, I'm going to subtract 0.5 to include that. And the X equal to A, the negative 0.5 to the 8.5. Now this forgot to do the less than, A less than X, less than B, but you can consider that the very same thing as A plus, here's the A plus 1 less than, so if it was A less than X, consider that A plus 1 less than or equal to X, and you kind of get the very same thing here. So let's do this another approximation. The statistical abstract of the United States reported that 66% of students who graduated from high school enrolled in college. 100 high school graduates are sampled. Let X be the number who enrolled in college. Find the probability that X was less than or equal to 75. So this is 0, 1, 2, 3, all the way up to 75 is that probability of any one of those versions would work. Okay. So our number of trials is 100. Success, P is equal to 0.66. N times P, 66. That's bigger than or equal to 10. N times 1 minus P, 34, bigger than or equal to 10. So we can do a normal approximation. Here's the mean, the N times P, that's the expected value. The standard deviation, N times P, 1 minus P. 4.73709. And I'm going to use the probability is, here's the statement, the probability that x less than or equal to 75. So I'm going to use correction, and I'm going to add 0.5 to the 75 to include that 75, and then using the tables or technology, probability of 0.9775. Okay. So that's using, so we have the exact method to do binomial probabilities, binomial distribution that we learned from the last chapter. But this gives us another method when the sample or the number of trials are large. This just gives us a quicker method than having to go through and calculate all those individual probabilities if we're going to do cumulative. And even without that, we still have to do all those calculations of NCX, N choose X, and P to the X, 1 minus P to the N minus X. So that should help. Hope you understood, followed along. See you next time.